Welcome back, everybody. Welcome back. I know we had the test last Tuesday, and you will have it back toward the end. The class that meets with me after this, at 12:45, you will get yours at that time. But the section that doesn't meet with me today, you will get yours toward the end of class. So you'll get it. So that's it. Yeah.
Are you gonna go over it?
Are you in the class that meets with me today? Maybe. We'll see. Yeah. So I have a few things to cover, and then we will, time permitting. Yeah. We'll see. Let's see here. My goal is to finish chapter 25 today, and chapter 25 is the chapter on the electric potentials and potential energy, right? And then chapter 26 is basically the same thing, but it involves some capacitors. So we'll do that next week, and then the following week, what do we have? So next week, yeah, exactly. Yeah, this is so here's what I did last time. I made sure I press airplane mode so it doesn't get interrupted. The recording did it, and then so just to review, I'm not going to go over the whole thing because I did it in discussion also one more time. So we had kinetic energy was always 1/2 mv squared. The work done is always defined as F dot dr from some R initial to some R final. If you have a conservative force like the electric force, then delta U will be minus W, and so or you can write it as minus over from R initial to some R final of F dot dr, right? So that was that. We also talked about, so this is the electric potential energy. Potential energy. And feel free to add the word electric potential energy because it's the electric potential energy, not the gravitation or elastic or whatever. So, and then we talked about the electric potential. Electric potential, what was the letter for the electric potential?
V.
So delta V, so it's supposed to be sharp, not U. The electric potential, just electric potential, no energy there. Right. Great. Potential is defined as just like delta U, it's F dot dr, but this one will be without the extra charge, so just E dot dr from R initial to R final. Okay. And then we mentioned some things about point charges. What happens when you do this integral for point charges? So let's also write that down. So for point charges, so if you have, let's say, a charge, let's say Q1 and a charge Q2, and they're separated by a distance R, then there is potential energy between them, and it is U equals to K, Q1, Q2 over R, right? K is the Coulomb constant, right? 9 times 10 to the 9, or 1 over 4 pi epsilon. Energy is measured in what units again?
Joule.
Yes, units or joules. Okay. And then the electric potential, when we integrated this for point charges, V turns out to be K. It would involve just one charge because it's integrating the electric field. So electric field is KQ over R squared, right? So when you integrate that, you get KQ over R. So we got KQ over R. And the units here are called volts. Okay. It's called the volt. So look at the U and V. What is something extra that U has where V doesn't?
Q.
Q. So if you multiply V by a Q, you will get U. Or if you divide U by a Q, you get V, right? So if Q is measured in joules, and I have to divide it by Q to get volts, so it will be joules divided by Q, which is in coulombs, right? So a volt is a joule per coulomb. Does that make sense? And the symbol for volt is V also. So symbol for volt is V, yeah. And another unit for notice also for the electric field, it's KQ over R squared. So a volt is like multiplying the units of the potential or the units of the electric field by a meter, right? KQ over R squared. So another unit for the electric field will be a volt per meter, and we have seen that in the lab. It was called V over M. I think people asked me last week, what is a volt per meter? What is V over M? It was a Newton per coulomb. So also note that 1 volt per meter is the same as 1 Newton per coulomb. And while we're talking about units, let me throw another one that I mentioned for my class yesterday, so I will mention to you. It's the electron bond. So another unit of energy, unit for energy is the electron volt. Looks like this. 1 eV, 1 electron volt, 1 eV is 1.6 times 10 to the minus 19 joules. So 1 eV is 1.6 times 10 to the minus 19 joules. Notice the 1.6 times 10 to the minus 19 looks like what?
Charge on an electron.
The charge on an electron or proton, right? Yeah. So the little e is basically this, and you multiply it by a joule. And it makes sense because, again, you divide joules by coulombs to get volts, right? So if you multiply volts by coulombs, you get joules. So anyways, 1 eV is equivalent to this many joules. Make sure I have mentioned everything I want to mention. Almost, I think, yeah. And since also, we'll do this more on the next chapter, since to get the potential energy, it involved integrating the force with a minus sign. You will see that, so this one is more on the next chapter, you will see that the force is minus du dr. And you can double check this. If you take derivative of this with respect to r, you have 1 over r. When you take the derivative, you get negative 1 over r squared, but you stick a minus sign in front of it, it becomes just 1 over r squared. And then the same thing for the electric field. It's minus d voltage or potential, dr. And again, kq over r, when you take the derivative, you get kq over r squared with a minus sign, but there is a minus here. So it makes it positive. You get kq over r squared, which is the voltage or the electric for a point charge. All right. Now, when can you use this formula and this formula? Every setup or a specific setup?
Point
Specific
charge.
setting. Huh?
Point charge.
Point charge. Good. So if you have a line of charge, don't just do this, right? You can't. It won't work. We will deal with those. So let's. By the way, a spherical charge. Once you're outside the sphere is like, it's 1 point charge in the middle, right? In the center. So for a sphere, it's also, let's say I have 2 spheres, 2 charged spheres, one sphere here and another sphere here. the potential energy between them will also be kq over r, kq1, q2 over r, but the distance is measured from the center of the two spheres, two centers of the spheres. So let's get some example with this one. Here it is. It says a proton is fired from far away at a 1 millimeter diameter sphere that has been charged to 100 nanocoulombs. What must be the initial speed of the proton to just reach the sphere? Just reach the sphere. So I'm going to put a little sketch here and then see what how we can solve it. So here's a sphere, and the sphere has radius 1 millimeter. No, the diameter is 1 millimeter. So the radius is half a millimeter, right? So let's say R is 0.5 millimeters. So you multiply by 10 to the minus 3, so you get 5 times 10 to the minus 4 meters. That is the radius of the sphere. And it's positively charged, right? The sphere is has positive charge. How much charge does it have? Well, it will have 100 nanocoulombs. So let me write that off. Capital Q, that's the charge of the sphere, is 100 nanocoulombs, and so that is 100 times 10 to the minus 9 coulombs, which is 1 times 10 to the minus 7 coulombs, right? That's the charge. Now, a proton is positively or negatively charged? Positive. So let's say I start my proton somewhere way over there, but that's as far as I can go on the board. So basically it's infinitely far away, and I fire it with a certain speed this way. As the proton approaches the sphere, by the way, the sphere will just be fixed. The sphere cannot move. The sphere is fixed, does not move. As the proton approaches it, does it speed up or slow down? Slow down, yeah. The sphere doesn't want it. It's positive. Doesn't want another positive next to it. So that's the intuition you should have. As it comes in, it will start to slow down. So what they want, this thing will have some V initial, some initial velocity. I'll put my V to be a little bit curly so it doesn't get mixed with the V, which is the voltage. Okay? So it will have some initial velocity that we don't know, but we would like it to, when it gets to the sphere, when it reaches the sphere, it will have a V final to be how much?
0.
Yeah, it barely reaches it. So we would like it to be 0. So we gave it just enough speed to reach the sphere. So when it reaches it, it will just barely touch it. Okay? It will not be like a collision or anything. So what should happen? The approach will be, you can have two approaches. You can use the force approach, or you can use the energy approach. Which one is better? Energy. Yes, it's always, almost always easier. So we'll say, by conservation of energy, the energy at the beginning should equal to the energy at the end. So the energy, by energy I mean the total mechanical energy initially, should equal to the energy at the end. Here's another problem. E now stands for what quantity? Energy, not electric field, so let's not mix that. So E here is energy. So you would have mechanical energy is the kinetic energy at the beginning plus the potential energy at the beginning equals to the kinetic energy at the end plus the potential energy at the end. Now, remember, potential energy is U between two charges is K Q1 Q2 over R squared. No, just over R. If they're very far apart, what's the potential energy?
0.
0, because you will be divided by infinity, right? Very far. You'll be divided by a large number. So this part here is 0. Now, when the proton reaches the sphere, it barely has any speed. So what is its kinetic energy when it reaches?
Zero.
Zero. So K final would be zero. So here's what happens. The kinetic energy at the beginning would equal to the potential energy at the end. And so that's set to be. Kinetic energy at the beginning, this part, is 1/2 mv initial squared, right? And the potential energy at the end is K, and then Q1 and Q2. The charge of the proton is E, right? The charge of the proton. So let me write it here. So one of them is the E, and one of them is the capital Q, right? One of them is the sphere, and one of them is the proton. So you would have E, Q divided by R. Now, how far apart are they?
Millimeter.
Here, right?
Oh,
I mean, that's far apart. So, from the center of the sphere to the proton, which is the radius. And it's actually 1/2 millimeter, right? Because the diameter is 1 millimeter, so 1/2 millimeter. So, it would be the radius of the sphere, in other words. So, you can solve for V now. So, you get V initial, initial velocity, will equal to 2 times K times E times Q divided by M square root. So you have 2, and K is always what?
9 times 10 to the
9 times 10 to the 9. And then charge of an electron?
Professor?
Yeah.
Are we missing an R?
About?
Yeah, denominator.
The initial equals square root of 2.
Oh, here, right?
Yeah.
Yeah, thank you. Right. Good. Okay. So 2K, and then what's the charge of an electron? 1.6.
Times 10 to the negative 39.
19. Charge. And then capital Q is the charge of the sphere, which is this 100 nanocoulombs. So it's 100 times 10 to the minus 9, or 10 to the minus 7, if you like. And then divided by mR. Now m here is the mass of what? Who is moving? Proton, right? Is the one moving. So what's the mass of that proton?
Oh, that's the times 10 to the negative 39.
If it were an electron, it would be something times 10 minus
27.
Yeah. It's 1.67 times 10 to the minus 27. That's for a proton. And then R is this, right? 5 times 10 to the minus 4. And then you have to square root the whole thing. And you might have noticed, here I wrote 100 times 10 to the minus 9, and then I simplified it to 10 to the minus 7, right? But here I decided to go back to my 100 times 10 to the minus 9 because I remember that there is 10 to the 9 and 10 to the minus 9. It's easier to just cancel them. And now what remains is you have to plug in the numbers. You plug in the numbers, and I will tell you the result. I think it's about 1.86 times 10 to the 7, according to the answer.
Like that.
Okay, cool. All right, 1.86 times 10 to the 7th power meters per second. Example? Alright. So now suppose I have a positive charge and a negative charge. Here's a plus, and here's a minus. Okay? So one of them is positively charged, the other one is negatively charged. This one is positive E. It's the charge of an electron. I'm sorry, the positive charge equal to the magnitude of the charge of the electron, and this one is minus e. The book calls them an electron and a positron. And they're initially at a certain distance. They're, I think, 10 to the minus 15 meters. 1 times 10 to the minus 15. That's our initial. That's how far apart they are. Very tight. Now, if they are at rest, what would happen to them? They can only get closer or farther. Yeah, they will get even closer. All right, does that make sense? So they're there. And if they're at rest, initially they would just collide. We don't want them to collide. So the question is this: what speed must I give this one and this one? So I want to give them equal and opposite speeds. So what should V initial? This one is also V initial. I want to give them enough speeds that they will go far away from each other. It's called the escape speed. They will escape from each other. This one will go to positive infinity, and that one will go to infinity on the other side. And I just want to give them just enough speed. You can always say I can give them 10 times that speed, and then just say I ensure that they will go away to infinity. But I want to give them enough speed so that when they reach infinity, they're barely moving, but they're infinitely far apart, so they cannot come back and hit one another. Is the statement of the problem clear? Okay, good. So when they're infinitely far apart, then what's their speed? 0. And what's their potential energy when they're infinitely far apart?
0.
0. So what's their total energy when they're infinitely far apart? 0. So by conservation of energy, then their initial energy must have been 0 also. So that's what I'm going to write. I'm going to write the energy at the beginning must equal to the energy at the end. The energy at the beginning will be the kinetic energy of the first object, the first thing. So let's call it K1 initial. One of them, let's call it 1, and the other one is 2, right? We have 2 kinetic energies, K2 initial. Plus their potential energy at the beginning, and that should equal to their kinetic energies at the end, K1 final and K2 final, plus their potential energy at the end. So again, by the statement of the problem, they will be infinitely far away. That means U final is 0. How do I know that? This is the potential energy between two charges. When they're infinitely far apart, it will be divided by a very large number. So that's 0. So this part, when they're very far apart, that's 0. And I want them to barely be moving when they reach infinity. So this one and this one are both 0. So that means the right-hand side is 0. Left-hand side. Left-hand side, we're assuming the book again, electron, positron, they have the same mass. So the kinetic energy of the first, I keep trying to say person, the first thing, the first object is 1/2 mv initial squared. And the kinetic energy of the second object, same mass, same initial speed, so another 1/2 mv initial squared. Their potential energy will be plus K times charge 1, which is E, right? And then what's charge 2?
E.
It's also E, but with a minus sign. Negative E divided by their initial distance. So initially they have positive or negative energy? Negative potential energy.
Negative.
Professor, is that a positron and an electron?
Yeah, that's what, yeah, the book. Yeah. So that's how I get 0. The kinetic energy is always non-negative, right? It's always either plus or at least it will be 0. But this one is negative. When you move it to the other side, it becomes a plus, right? Yeah.
So is the V initial for both charges the same?
Yes.
Can
That's what they want to give them. They want to give them just equal speed that they go away from each other. Yeah. So 1/2 mv squared plus 1/2 mv squared is just mv squared, right? So you get m v initial to the power 2. Yeah. And then here, when you move it to the other side, everything becomes a plus, so k, and then becomes e squared over r, right? E times e is e squared, and the minus sign goes away. And then r initial. So divide by m and take the square root. So you'll get v initial will be k e squared over m r initial square root. Now, we're given, it's an electron and a positron, you know their masses. It's an example from the book, so it's open book, so you're supposed to look up that number. If it's in a test, of course, you'll be given that number, but this one, we can look them up. So it's 9 times 10 to the 9 for k. E squared, so 1.6 times 10 to the minus 19. So you have to square over the mass. Do you want the mass?
Oh, I got it. It's 1.67 times 10 to the negative 31.
Almost. Times 10 to the minus 31, but it's something else.
0.36?
9.11. It's the one.
I scared with the last.
And then our initial is 10 to the minus 15 and square root. Okay, so you're supposed to plug in the numbers and get something. And that number happens to be 5 times 10 to the 7. Meters per second, of course.
Professor, how do you know K is 0?
Okay.
No, that guy-
Because they said, you want to just give them enough speed, that they would be barely moving at anything. You can always give them extra speed, so when they go to infinitely far away, they will still be moving. But we want to give them just enough speed that they will be infinitely far away, and they will stop moving.
Or stop them.
Yeah, or barely moving.
Okay.
Yeah. So it says, what minimum speed must each have when they are this one, 10 to the minus 15 apart? Oh, I'm sorry. Was it 10 to the minus 15? I think it was 10 to the minus 13. 10 to the minus 13, right? Okay, yeah. So, yeah, 10 to the minus 13. So if you plugged in the numbers, 10 to the minus 13. Yeah, otherwise the speed would be even higher. One more of these. 1 meters, of course. So now I'm going to have the following. Here's the next example. Three electrons. Here they are. There is an electron here. So they're electrons, right? So they have the charge of an electron and the mass of an electron. And there is another electron here. There is another electron here. And distance is, let's look it up. I think it's 1 millimeter. Yeah, it's 1 millimeter. 1 millimeter. 1 millimeter. Yeah. And so this electron is fixed, cannot move. This electron is fixed, cannot move. But this one is able to move. If I started exactly in the middle between them, what happens to it?
Stay there.
it stays there. And the reason is because the net force on it would be zero. If I started exactly at the middle, what does this electron do to this electron? Pushes it away. What does this one do to it? Pushes it up. Since it's equidistant from both of them, net force is zero. So it will just remain there. Okay? Now, is this a stable equilibrium or unstable? Meaning if I perturb this electron a little bit to the left or to the right, does it come back, just kind of oscillate, or does it just move away? It will move away, because if you move it here, this one will apply a force on it in that direction, and this one will apply a force, if it's right here, right? This one will apply a force on it in this direction, so there will be always a net force in this direction. And so it will just spring and go through it. Alright? So, the question is, if the electron is displaced a small distance, let's say we move it slightly, the question is, what would its speed be when it's infinitely far apart? So if we move it slightly, okay, if I move it slightly, so it's no longer in equilibrium, so it starts from what speed? If I move it slightly and let go. Okay, so I let go, so initially, V initial will be zero. And the question is find V final when our final is infinite, right? It moves it to very far away. So what would this be? So we can use conservation of energy again. Conservation of energy. We would say the energy at the beginning should equal to the energy at the end. And that's equate. See what happens. So before I go on, is the statement of the problem clear? You have an electron here, and electron here. This electron, these two are not free to move, they're fixed. This one can move. If you keep it exactly at the middle, it will remain there. Net force is zero. If you perturb it a little bit to the right, then it will start moving away, and it will only keep getting farther, because there is a net force always to the right. So it will just go. It will keep going. Now the question is, when it gets to very far away, infinitely far away, what is its kinetic energy? So we will figure it out, right? We'll have to figure it out. So we'll have this. The energy at the beginning, so the energy at the beginning should equal to the energy at the end. That's conservation of energy. The energy at the beginning will be the kinetic energy at the beginning plus the potential energy at the beginning. And it should equal to the kinetic energy at the end plus the potential energy at the end. Now at the end, when it's infinitely far away, what is the potential energy? Zero. Because it's KQ over R, right? KQ1, Q2 over R. So you'll be divided by a large R. So this one is zero because it's infinitely far away. Now, we're after this. That's what we're trying to find. The kinetic energy at the end. What's the kinetic energy at the beginning then?
Zero.
That one started being zero. You see, the potential energy at the beginning is not zero. And so this right hand side cannot also be zero because they're equal. So this is not zero, this one cannot be zero. So let's see. On the right side, for the kinetic energy, it's 1/2 mv final squared. Let's see what the potential energy is. This electron, do I only have two charges? Do I just have KQ1, Q2 over R?
No.
No, there's potential between this one and this one, and between this one and this one. So I have two potential energies, so you would have the potential energy would be K, and then charge 1 times charge 2 divided by R, by R initial, which is what, 1 millimeter, right? And then K, Q1, Q2 over R initial, which is also 1 millimeter. So K, Q1, Q2 over R, it's also 1 millimeter. Now what are the charges?
They're all E1.
They're all electrons, so it's negative 1.6. So it's negative E.
Oh, right.
Yeah, it's minus E. minus E, minus E, and minus E. Now, when you multiply them, it becomes a plus, right? Minus times minus is a plus. So from here, you would have KE squared over R plus another KE squared over R, so that's 2 KE squared over R. So you would have 2 K E squared over R equals to 1/2 and d5 squared. Multiply both sides by 2, divide by the mass, and so forth. So get the final, and be 4 K E squared over M times R squared. Let's see what the numbers are. 4, and then K is what?
9 times 10 to the 9.
10 to the 9. And then E is
1.6 times 10 to the
10 to the minus 19. But I don't just have E, I have E squared, so don't forget to square that. And then the mass here is the mass of an electron. And it is? Does anyone remember?
9.11 times.
Good. And then R is 1 millimeter, right? So 10 to the minus 3 meters. That's R, right? 1 millimeter. Yeah. 10 to the minus 3. 10 to the minus 3. But don't forget to square root the whole thing. And according to the answer, it's about 1,000. Yeah.
You said velocity final is infinity and all. Is that
This one?
above that?
Oh, question mark. Yeah, no, not infinity. Yeah.
Why we don't have the potential energy between the top electron and bottom one?
Because there is energy between them, right? And at the end, it's the same amount of energy between them, so it doesn't change. Does that make sense? So let's say at the beginning, you're saying, why isn't this potential energy included, right? Let's say the potential energy here is 5, right? Let's say it's just 5 joules. So it's 5 joules at the beginning, so I will add 5 to this left side, right? And then how much will it be at the end? Still 5, right? So it doesn't matter. The only change is this one because it moved. Yeah. But good point. I overlooked that and I just, yeah. Yeah.
Could you also think of that as like, it's not affecting like the electron you're looking at, so you don't have to include it?
Is it not?
Like the same question, where you don't include like the top and bottom one, because it's like, it's not affecting like the thing that's like moving, so it
Yeah,
matter,
yeah,
right?
yeah, exactly. So there is no change from these two. They're wherever they are. So, yeah, their positions have not changed. So hopefully you get 1,000 here, or 1,006. I think I got. I will write 1,000 meters.